You can see this.
Yep. So welcome everybody. We are really happy today that we have Professor Niall Friel with us. So Niall is a professor of statistics. So he's a really active member in our society. His research interests include intractable likelihoods, statistical network analysis, Bayesian statistics, and of course MCMC methods. And today he will be talking about assessing competitive balance in the English First Division Premier League for over 40 seasons using a stochastic block model. So Niall, it's a pleasure to have you with us today, so you can start your presentation.
Thanks very much, panelists. It's a real pleasure to present to you today. So the talk is, as panelists has told us, is about assessing competitive balance. And to do this, we're going to use a network model. So the talk is in collaboration with Francesca, who's a PhD student at in mathematics at Warwick, Vasiliki, who was a former master's student in Athens, and Yanis, who you all know. So it's been a real pleasure working on this project because not only kind of combines some statistical modeling ideas that I'm interested in, but also football, which is a big passion of mine. And I guess the final thing that's been great about this project is that it's the first that myself and Yanis have collaborated on. We've been friends for many years, and it's nice to see this project finally realized. All right, so also it's a nice opportunity to present a picture in the background of my team, which is Glasgow Celtic. So it's very rare for me to present a stats talk to introduce such a picture. All right, time to get going. So to give a bit of background, this idea of competitive balance, it's one that has been, sort of widely understood in kind of public discourse, let's say. The idea that it's important to have a competitive league so that public are interested, and just that it's generally a good thing to have in a sporting competition. So here's a tweet that I picked up just last night, and it's a discussion about whether the Bundesliga needs to introduce playoffs in order to make the league interesting. So Bayern have won the Bundesliga for many years in a row, and the idea there is that that league is not so competitive. Another article, which written by this guy Michael Cox, who's quite a big name in football analytics. He's asking, it's from the Athletic, the online magazine, how can we make Europe's big leagues more competitive? And basically his argument is that in most of the European domestic leagues, we know already who the title winners will be. And as he says here, it's a situation we've become accustomed to. The rich clubs wrapping up their leagues by the turn of the year. So yeah, this kind of notion of competitiveness is one that the public well understands. And the idea of the talk today will be to try to place this in a statistical setting, and in particular to see how our models apply to the English Premier League over 40 seasons. So just to tell you a little bit about the English Premier League First Division. So it's one of the oldest football leagues in the world. It dates back to 1888. It rapidly grew. So the second division was introduced in 1892. And today it consists of 4 divisions. But actually underneath those 4 divisions, we've got a whole kind of pyramid system of so-called non-league teams. And one of the features of it, as for most football leagues, is that you have this possibility of getting promoted to the division above, and teams that finish towards the bottom of their league would get relegated to a lower division. So there's a huge pyramid system underneath this English Football League. All right, so there's been many changes over the years, but maybe the most significant has been the introduction of the Premier League in 92-93. And one of the things that this brought with it is a massive increase in revenue. So for example, the first TV deal between the Premier League and television companies generated around £40 million. And the latest TV deal between 2016 to 2019, that increased to 5.1 billion. So huge TV revenues are being generated. Okay, so to introduce the statistical element of this, so competitive balance, so it's a feature that any sports league would like to have, and it tries to capture the notion that there's unpredictability in the outcome of games. And the particular slant that we take on this is to place this problem in a network analysis framework. And the objective is to probabilistically cluster teams in a league so that teams within a particular cluster or a block are balanced in a certain sense that we'll explain later. One of the key issues for us will be to assess the uncertainty in the number of blocks, and also to estimate which teams are allocated to which block. So block being synonymous with cluster, basically. So what we do then is we'll apply our model to every season in the English Premier League / First Division from 78-79 through to the most recent season. And to look ahead a little bit, one of the key findings of our results is evidence that suggests that the old First Division Premier League was a reasonably balanced two-tier league, reasonably balanced league, to one which is now a two-tier league, and that happened around the 2000s. So that's a kind of look ahead to what we'll conclude at the end. All right, so competitive balance has been in the literature for some years, and maybe one of the most widely used but most basic measures of competitive balance is this so-called Hirschmann index of competitive balance. What it does is it's based on assessing the measure of spread of points share in a given season. So if we suppose that team I scored SI points over the course of a season in a league involving n teams, then you look at the points share of team I, defined as quite simply SI over the sum of the SIs. And then that this Hirschmann index is n times the sum of the PI squareds. So it's a measure of the spread of this vector P1 up to Pn. Okay, and this is a sum of these PIs will obviously add to 1. When each team has an identical proportion of points, so that PI is 1 over n, then we're in a kind of ideal balanced situation. Then the HHICB is 1. In a similar way, another approach is to use the concept of relative entropy. So relative entropy is one that will aim to measure the disorder, or the order in this sequence of PIs. Relative entropy is defined as PI times log PI summed over I, and that's normalized by log 1 over n. So in this case, the relative entropy statistic takes a maximum value of 1, and that's in the case where PI, the proportion of points for each team I, is 1 over n. So in this case, lower values of relative entropy suggest a more imbalanced league. All right, so here's the data for both of those statistics, the Hirschmann index and relative entropy across each season. So for the HHICB, we see that it's increasing over time, generally, and that's consistent with the hypothesis that the Premier League has become more imbalanced over time. And relative entropy gives the same information, just that now we interpret lower scores as meaning more imbalance. So they're both conveying exactly the same information. Okay, you know, to criticize those approaches or to talk about their limitations, maybe. They're both univariate statistics, so it's hard to make any qualitative conclusion about whether a season is balanced or not. And if we see some evidence to suggest that a season is imbalanced, it would be really useful to give an indication of the nature of the imbalance. So which teams, if any, are stronger than the remaining teams. And one of the points that is quite important for what follows is that the approaches don't explicitly model the relational nature of the data arising from a league. So by relational data, I mean the fact that in a league, Team A will play Team B. So it's relational in that sense. So the network model which we propose gives us information about the quality of the leagues and also the relative competitiveness. And generally, although the methods we propose, they're a lot more computationally demanding than the two indices and other similar type indices in the literature. But they're richer in terms of the results and the conclusions that we can make. All right, so this is pretty much where the idea for the project began. So if we think about what I'm calling a results matrix, so it's often how we see the entire set of results for a league presented. So a lot of people will be familiar with this type of presentation of the results in the season. And how you read this is the teams on the rows. So I'm pointing to Arsenal here. So Arsenal played Bournemouth. So Arsenal were at home, Bournemouth were away, and Arsenal won 5-1. In the English Premier League, teams play each other twice, home and away. So in the reverse fixture, when Bournemouth played at home against Arsenal, who are now away, Bournemouth lost 2-1. So the diagonal entries are all blank because a team can't play itself. And what we do is we basically say to ourselves, can we summarize this entire table by coloring the entries of each result as green for a home win, red for an away win, or yellow for a draw. And that's what we do. So we summarize in this categorical way the entire results table. And I said this is where the project started out, because actually I gave a seminar in Athens a few years ago, and it was on a different but related topic in network analysis. And after discussing afterwards with Yanis, he said, surely you can apply a network techniques to this type of tabular data. And really that's where the project started from. Okay. So what do? We've got three categorical variables. We have a win, a draw, or a loss, and we're denoting them with the numerical values 1, 2, or 3. These are just categorical values, so they've no numerical meaning other than just labels for the win, draw, or loss, respectively. So each season then is summarized in a matrix W. We call this the results matrix, and each entry, Wij, takes one of these three categories, 1, 2, or 3, corresponding to a win, a draw, or a loss. And I should emphasize that Wij means when home team I plays away team J. Okay. So where does the network analysis come in? Well, the network analysis comes in because we can think of the results matrix as an adjacency matrix of a directed network. So each node in the graph or in the network represents a team, and an edge from node I to node J, that'll represent the outcome of the match when team I plays at home against team J. And here the edge takes again the value in this set 1, 2, or 3. These are the categories again corresponding to home win, draw, or away win. So here the network is dense and complete because every team plays every team twice. So there's a directed edge from I to j and from j back to I. And this is in strong contrast with what's usually observed in social networks, where we normally see a lot of sparsity in the adjacency matrix. So for example, in a friendship network, for example, between n individuals, if we pick two individuals at random from that network, they're likely not to be friends with each other. They're likely not to be connected. So we get a sparse network in general. Here we get a complete network. Okay, and the fact that we can represent the results matrix as an adjacency matrix allows us to place this in the context of social network analysis. And the idea is that we want to find some structure in the results matrix. We'd like to find groups of teams that have similar outcome patterns in terms of win, draws, and losses. All right, so we now get on to the topic of network modeling, and in particular, stochastic block modeling. So the story with a stochastic block model, it begins with a much more simpler model called an Erdos-Renyi random graph model. And that's a simple model for binary random graphs. This is one that assumes that Yij, which is the dyadic variable when node I possibly connects to node j, and that's distributed as a Bernoulli with probability p. So there's basically an edge between node I and node j with probability p. And it assumes that all edges are independent Bernoulli random variables. So a very strong and usually not correct assumption in practice. So it's a very simple model, and the number of observed edges E, it turns out to be a sufficient statistic, and the likelihood can be expressed as simply a product of these Bernoulli random variables. So p to the power of E, 1 minus p to the power of the total number of possible edges, which is n choose 2 minus E. Okay. Now, the stochastic block model, and this is the one that we want to develop for our competitive balanced model, proposed by Nowicki and Schneiders back in 2001. And it's been extended in several directions since then. So it's a very popular model for network analysis. Turns out to be a finite mixture model. And what the SBM does is it stochastically partitions the nodes into k blocks. And k is a random number. So we don't know in advance how many blocks would be best fitted to our particular network. The point here is that the nodes within each block are modeled as an Erdos-Renyi random graph. So that's connecting to the more simpler model. And the nodes themselves are characterized by a latent cluster membership variable. In other words, each node has some latent variable telling you what block that node belongs to. And the probability of observing a particular edge, in this case, is determined only by the clustering variables of the two nodes. Meaning that if we know which block node I is in, and we know what node block J is in, then their connection probability will depend on those two allocation variables. Okay, so putting a bit more detail on this, the SBM assumes that nodes are partitioned into k clusters, and k is an unknown number. The cluster membership of each node is denoted by this variable Zi. So Zi takes values in 1 up to capital K, where capital K would be the maximum number of clusters considered. And Zi is defined so that the probability of Zi equals to G is alpha G, where G ranges from 1 up to K. So if we know that Zi is in block G, and we know that Zj is in block H, then the chance of observing an edge Yij is given by PGH. Again, once we know this latent membership for Zi been in block G, Zj been in block H, the chance of connecting I to j being connected is determined by PGH. So specific to I bin in block H and j bin in block I in block G and j bin in block H. All right, so we therefore need a k by k matrix of block connection probabilities to allow for each possibility for a node bin in block G and the other node bin in block H for all possible values of G and H. That gives us this k by k matrix. All right, so then given, again, Zi equals to G and Zj equals to H, we draw an edge from a Bernoulli distribution with probability PGH. In other words, Yij given the membership probability for node I and the membership variable for node I and the membership variable for node J is a Bernoulli with probability dependent on G and H. So it's quite a generative model and how it's described here. Okay, so here's a simple wee picture of this situation. So here's a network. The edges tell you what node is connected to what. You don't know the block structure here, but I've colored them in the second column here to say that the blues are one particular block and the reds are another block. And when we rearrange this network, this is the same network just with 3 different visualizations. So in the last picture here, we've rearranged the network to show that the red block has got a strong kind of connection probability among themselves. Likewise, the blue colors, but very little connections between the red and blue blocks. That's the essence of an SVM model. Can you model, say what the colors on each of these variables are, according to what block they belong to, and then estimate the probability of connection within each block and between each block. Okay. All right. Yeah, so the title here is one of the things that you don't know is the number of things that you don't know. Again, sort of a quote from, I think Peter Green some years ago. And it basically kind of captures the idea that for these latent cluster models, the number of clusters is quite an important thing to understand. So yeah, so from a statistical perspective, a source of uncertainty is the number of blocks or clusters, K. And statisticians are used to dealing with this issue. And it's non-trivial in the case of an SVM, but again, it's one that statisticians are familiar with. And there's a whole bunch of techniques that one could use to handle this situation. So EM, reversible jump, various types of MCM and model selection criteria, and so on. All right, so getting back then to our results matrix network and a stochastic block model that we want to develop for it. So the aim of our SVM model is to partition the N teams in the league into K blocks in such a way that the probability of a win, a draw, or a loss for the home team is more or less similar for any 2 teams in the same block when they play against each other. That would mean to say that we aim to find a block such that we've got balance for teams within that block. But equally importantly, the probability outcome when any team from one block plays at home against another team from a different block, it would also have a similar probability of a win, draw, or loss for any team in that one block playing against another team in that different block. And a crucial point is that the probability of a given outcome will depend on the block membership, effectively the blocks to which each team is assigned. And one of the key objectives for us is to infer the most likely value of K. And in particular, if we deem that K equals 1 as most support, then we get some evidence that the league is balanced. Okay. All right, 2 main assumptions that we make. The first is that for a K block model, each node for team I equals 1 to n, belongs to one of the blocks with membership allocation label zi equals 1 up to k. We assume that the distribution of the outcomes, yij, are conditionally independent once we know the latent cluster membership vector. Again, what block each of the teams are allocated to. Okay, so we can then start to do some modeling now. All right, so let's suppose that team I is in block K and team J is in block L. And let's now suppose the probability of, again, a win, a draw, or a loss when a team in block K plays at home against a team in block L. Let's assume that that's governed by this PKL vector. So P1 will give the home win probability, P2 will give the draw probability, and P3 will give the loss for the home team or the win for the away team probability. And of course, these three numbers will add to 1. All right, we then model that outcome as a multinomial with that probability vector, just one outcome, right? So basically, the probability that yij equals omega, given again that I is in block K, J is in block L, and given this vector, is P omega KL, where omega takes 1, 2, or 3, according to win, draw, or loss. So for example, let's pick an example where team I is Tottenham Hotspur, and suppose they're assigned to block 1, and they play at home against team J, who's Crystal Palace, and they're assigned to block 3. Let's suppose that we've inferred that P13 is 0.6, 0.3, 0.1. If we observe Spurs beat Crystal Palace 2-0, that means it's a home win. So omega equals to 1. And the likelihood of that, given the allocation probabilities of Spurs to block 1, Crystal Palace to block 3, and our probability vector, is then just 0.6. So it's quite simple, right? But the issue for us is always what are the allocation, what blocks are each team's allocated to, and what will be this PKL vector. Okay, all right. We're going to assume now that the entries of Z, this is the allocation vector, are independent and identically distributed following a multinomial distribution. So Zi given theta and k is multinomial 1. So it's just one value. So Zi is a single variable. Given theta, where probability that Zi equals to k, given theta is theta k. And that's the probability that node I belongs to cluster k. Theta k must be positive, and the sum of the theta 1, 2, up to k must be 1. So in this way, the distribution of the partition of the n nodes or teams into k clusters conditional on this theta vector is then just this product of multinomials. We got to put a prior on theta itself. We're going to assume a vague conjugate prior following a Dirichlet of dimension k with a vector of concentration parameters a gamma. So theta given k is Dirichlet. And we're going to make the simplifying assumption that the concentration parameters are all set to 1, yielding a uniform prior, basically, for theta. All right, we have this more complicated quantity, P, for each entry of P, it's K by K, and each entry of this matrix is itself a 3-dimensional vector. Again, PKL is the probability that when a team in block K plays at home against a team in block L, the outcome is a home win, so that's P1, a draw, or a loss. And the sum of these P omega KLs also adds to 1. Okay. Now we model the actual data, so the relational pattern of the results matrix Y, again, conditional on the latent allocation Zi, Zj, as also multinomial. So we can write that as a multinomial Yij, just one outcome with this pKl vector. And we can write this in the following way. This power here just involves an indicator variables. It just picks out which block a particular I belongs to, and it allows us just to write it in this very general way. But it will just reduce down to a simple multinomial once you know the allocation probability, the allocation for each team to each block. Okay, that's the probability for Yij. We've assumed that knowing the Zs, the Yijs are conditionally independent. That's one of our assumptions. And that allows us to put together a likelihood for the entire results matrix given the Z vector and the P matrix. It looks a little bit complicated, but in practice, it's very, very simple because these indicators, they're indicators that take one when the argument is satisfied. Just reduce things down to something very simple. All right. Some more priors. The entries of P, they're modeled as mutually independent, and each pKl follows a conjugate prior from a three-dimensional Dirichlet, as so. And all of these hyperparameters, beta 1, beta 2, beta 3, they're also set to 1, again leading to a uniform prior distribution of pKl. All right, the prior for K, we treat that as distributed according to a zero truncated Poisson random variable with rate equal to 1. The reason we do that is that it leads to a prior on K proportional to 1 over K. And that's accommodating the fact that if we have a K block model, the labels that we assign to each block are completely arbitrary, and they can be permuted. And they can be permuted in K factorial ways. So it makes sense, I think, to make that prior proportional to 1 over K factorial. And it's something that is done in the literature on finite mixtures as well. All right, we're now able to write out the full joint posterior of our model. So P of Z, P theta K given Y, proportional to likelihood times a whole bunch of priors. Now, our primary interest is in the marginal distribution of the latent allocation vector Z and the number of blocks K. And it turns out, because of our choice of multinomial Dirichlet likelihood for f of y, as I'm pointing out here, and p of pk, allows us to do this integration here in the second equation. Similarly, Z follows a multinomial likelihood with a Dirichlet prior. It too can be, it too is one for which conjugacy applies, and theta can be integrated out in this case. So actually, just to maybe make this a wee bit clearer, this entire joint distribution can be split into two integrals. In the first integral, because of conjugacy, we can integrate out P, this P matrix. In the second equation, we can integrate out the theta variable. So we're left effectively with a joint distribution, a posterior for Z and K. This makes the computation a lot easier. But it's not a kind of necessary feature of the model, but it's just one that we exploit here. Just to write out what the Bayesian, what the posterior distribution looks like, it has this form, okay? And the kind of, the thing I just maybe just to dwell on is that one of the terms here is what's called NKL omega. And what that is pretty simple. It's basically the number of teams in block K, teams in block L. So when those two teams, when a team in block L, sorry, let me say it, start again. When a team in block K plays a team in block L and the outcome is omega, this number is the total number of instances of that situation. Okay, so omega can take values 1, 2, or 3. K can take values 1 up to K, and L can take values also 1 up to K. The other term you see is this NK, and NK is basically the number of teams in block K. So you get quite a parsimonious posterior distribution for Z and K.
Sonal, can I ask a question?
Sure, Panos, please.
So you are doing something like an allocation sampler here?
Eventually we will, yes. Yeah.
Okay.
Yeah,
Nice.
exactly. That's
Okay.
right. We want to basically allocate each team to one of the K possible blocks, and also learn about K at the same time.
Yeah. Yeah. Nice.
The
nice.
distribution over Z and K.
Great.
Great. No, thanks for that. All right. So the MCMC scheme, I'm not going to go into any details, just to say that it's quite a standard algorithm, I suppose, for this type of situation. We have a particular move type that inserts or removes an empty cluster. That changes the current state of K, but doesn't change the Z vector at all. We have a metropolis within Gibbs move, and that updates all of the elements of Z, but it doesn't change K. And then we have a metropolis Hastings move that is like an absorb or reject move, and that affects both Z and K. One of the things we need to be aware of is the label switching issue. So the allocation vector, it's not identifiable by the model because of the invariance of the cluster labelings and the permutations of those. So we use an established algorithm by Karp and Eto and Tot to undo the relabeling, basically. All right, so let's get on then to the results. Okay, so as I said, we're interested to analyze every season from 78, 79 through to last season. We're particularly interested to explore if the league has become more or less competitive over time. Sort of side question, but an important one we think is to see whether there's evidence of a big six group of teams. Are there a set of teams that persist in the top block over time? So what we're going to do first of all is look at the 2018-19 season in some detail, because this will allow us to present some of the salient or the important features of the model. Okay, this was a season that Manchester City won, and they're pictured below here. What we found is that a two-block model had overwhelming support with about 97% probability. Here's the league table, where we have Man City on top with 98 points, through to Huddersfield, who were relegated, with Fulham and Cardiff City with a certain number of points. On the last column here, we're presenting the probability of each team belonging to the top block. So we see there's quite a kind of tightly grouped teams that have a high probability of belonging to the top block: Manchester City, Liverpool, Chelsea, Tottenham Hotspur, Arsenal, and Manchester United. And then we get a bunch of teams that have very small probability of belonging to the top block. What is interesting is that the points ordering doesn't need to correspond to the ordering of probability according to the top block. For example, Arsenal had 70 points and they have a 90% chance of it in the top block, while Tottenham Hotspur has 71, which is more than Arsenal, but they have a smaller probability of belonging to the top block. Manchester United have 66 points, and they've a higher chance of belonging to the top block than Tottenham Hotspur, for example. We're going to look a little bit at this kind of situation with these three teams in detail in a moment. But right, I think here's a kind of interesting way to think about this model. Here's the original results table for season 18-19. The teams are listed simply in alphabetical order. I'm pointing to the results matrix in figure A. Right, again, just to remind you, green means the home team won against the away team who are listed in the column. Yellow means a draw, and red means that the home team, which is listed in the rows again, lost. So what our model will do is it will basically permute effectively the teams in this table. It'll permute the rows and columns according to what team is in what block. So if we list all the teams in figure B, if we list all the teams in the top block first and followed by the teams in the second block, and I've got a solid line kind of denoting boundaries between one block and the next, you see an interesting kind of pattern developing, as I'll point out. Again, all we've done is the algorithm has basically said, it amounts to basically permuting the rows and columns of this matrix according to membership of the first and second block. All right, here's this reordered matrix according to the first 6 teams in the top block and the remaining 14 teams in the second block. So let's focus on the top block. And what you see here is that there's a relatively kind of balanced set of green, yellow, and red colors, more or less, right? So these teams are quite competitively balanced among themselves. This again is the top block, within top block. Excuse me, I'm too fast. This is the within bottom block. And here we also see, reasonably random coloring of green, yellow, and red, suggesting that the teams in this bottom block are quite balanced. What's important is that when we look at the quadrant here, which is when the home team in the top block plays an away team in the bottom block. Now we see that we don't get this kind of random ordering anymore, coloring anymore. We see mostly green colors because the strong team at home typically beats the weaker team away. So the partitioning has made sense. We've uncovered this pattern basically. When the away team at home, when the team in the second block at home plays against the weaker team away, we now see mostly red colors, okay? Because the win-draw loss probability vector when a weak team in the second block plays a strong team in the top block is similar, but it's shown mostly red colors. So overall, we think that our partitioning has basically revealed this nice structure. That's kind of one of the interesting things I think about this model, but what it tries to do. Okay, just to kind of go back over and try to explain this situation where Spurs, Arsenal, and Man United had their points totals don't quite correspond to the probability of membership to the top block. Let's kind of look at that in a little bit more detail. All right, so we've just picked out the head-to-head table when these 3 teams play each other. And the important point here to say is that Tottenham's record against both teams. So Tottenham drew against Arsenal, they lost against Man United at home, they lost to Arsenal away from home, and they lost to and they beat Manchester United away from home. So their record is 1 win, 1 draw, and 2 losses. And that's the same as Man United's, but it's worse than Arsenal's record. So Arsenal have a win against Spurs, a win against Man United, and 2 draws away from home. So that's basically consistent with Arsenal being estimated a higher posterior membership in the top block than Tottenham, even though they've got a lower overall position, even though Tottenham have a lower overall position. And this is kind of getting at the idea that we're modeling the relational outcomes when teams play each other. Okay. Yeah, so this is the picture when we look at the 40 2, I think, seasons overall. And what I'm presenting here is that the probability of there being 1, 2, 3, or 4 clusters, probability is multiplied by 100, basically. And this kind of bluey color means that the season that year has most probability of being a 2-cluster model. And this sand color is the probability that a 1-cluster model had most support. And it's kind of convenient that the results are split into 2 halves. Because in this first half, we see that there's a lot of seasons where a 1-block model has a lot of support, right? A lot of sand colors here. There's also quite a few seasons where there's a 2-block model. But for those seasons where there's a 2-block model, often there's quite kind of equal support between the 2 possibilities. So 84, 85, a 1-block model has a 44% chance of being a 1-block and about a 55% chance, 56% chance of being a 2-block model. 87, 88, all right, mostly a 2-block model in this case. 1991, you can't really decide between a 1 and a 2-block model here, and so on. So the story is usually a 1-block model, sometimes a 2-block model, and sometimes kind of roughly equal support between the 2. That's for the first half of the season. Okay, and actually, I suppose it persists really up until 01, 02, 02, 03. But what's interesting is that during the Premier League era, we see a totally different story, because now the 2-block model starts to persist, right? But not only that, but there's a really high posterior probability of a 2-block model being most supported. Now, there are two notable exceptions. The first is 15-16, and that's a pretty famous year for the Premier League, because that's when Leicester City won the league, and Leicester City overcome all the odds, and they're it's sometimes said it's the greatest underdog story in sporting history. So that season was a bit different. All right, what we've tried to do here is to dig a little bit deeper into the results in that previous table. And what we do here is for each season, we present a jitter plot of the probability of each team belonging to the top block. So each point along each column here corresponds to a team and their probability of membership to the top block. So what I could maybe do is kind of draw your eyes towards looking at the left-hand side of this plot, around where I'm pointing to with the cursor, right? And what we see is that for many seasons, most teams have a high probability of belonging to the top block, suggesting that that entire season was competitively balanced. Of course, it doesn't happen every season. There's some seasons where there are quite a few teams, such as 78, 79, 79, 80, probably the season 80, I think, where there's a chunk of teams that have relatively low probability of belonging to the top block. Again, this kind of sand color means it's a k = 1 model. Blue color means a k = 2 model. All right, but when we look at 2002-03 onwards, we see a different story. We see that there are now a bunch of seasons where we get a bunch of teams that definitely are not, have got a really low probability of belonging to the top block, suggesting that there's an imbalance in the league competitively. Okay, that's the main kind of message here. But also, if you look at the number of teams each season that have got high probability of belonging to the top block, there's generally quite a few teams in that block, a small number. So we see a kind of transition from a balanced league, more or less, to an imbalanced league. That's what this picture is trying to convey. We can go a little bit further and we can ask, what is the best estimate of the size of the strongest block each season? And this is what we're presenting here. And again, kind of point out that around 2002, 2003, the number of teams in the strongest block, it's denoted by the number on top of the bar, basically. It's generally in the 20s, meaning generally competitive leagues for the early part of the study for the first 20 odd seasons, while 2003 onwards, the number of teams in the strongest block is generally a small number. This is the Leicester season, the Leicester City season win here. And here, I'm not sure, I think it was Manchester United that won the league that year. But generally the message is a two-block model with a small number of teams in the top block. Now, we reran the model for last season. And interestingly, the number of teams in the top block last season was 15. And last season it was an exception, right? It was an exception because COVID played had quite an impact. The grounds were empty, and generally it was felt that the league was a lot more competitive, and that's borne out by our results here. So I think there's an emerging literature on how football leagues and sporting leagues in general were impacted by COVID in terms of absence of crowds and things like that. And I think our results here kind of are aligned with that. All right, so just to summarize then, so these results indicate that there's most support each season, a posteriori, for either a one-block or a two-block model. But the number of seasons where a two-block model has most support increases significantly over the past 2 decades. So in particular, over the first half of the study period, there is no strong support for either model. So some seasons, there's broadly equal support for a one or a two-block model. But around 2000, or let's say maybe 2003 would be more precise, more or less, there's typically most support for a two-block model. But that posterior probability for a two-block model is over 0.8 for almost every season since 2003, 2004. That's given us strong evidence that the league has become more competitively balanced since then. All right, I just want to maybe kind of go quite quickly through this slide. It's trying to ask, is there, you know, a group of 6 teams that are persistent in this top block over time? We're looking simply at the second half of the study here, and a tick tells you if that team was in the strongest block. And generally, these 6 teams, Arsenal, Chelsea, Liverpool, Man City, Man United, and Spurs, more or less for the past decade, with some exceptions, have been mostly in that top block. For the second half of this, the second decade, the early 2000s, actually, Man City weren't in the Premier League, and for seasons that they weren't in the top block. Likewise, Spurs, or Tottenham Hotspur, also generally weren't in the top block, but from the 2010 season onwards, they were. So there's evidence that there is an emergence of a big 6 group of teams. Again, last season is an outlier. We have 15 teams in the top block. There's probably an outlier in itself because of as I said, the COVID restrictions on crowds when present. But let's see what happens into the future on that. All right, so here's where we finish up then. So our analysis then shows that, broadly speaking, the league was quite balanced from 1980 to 2000. But then we see this kind of transition to a more imbalanced league. So 2 blocks are more probably posteriori from then. We see some evidence of the emergence of a big 6 group of teams since around 2010. And just to finish off, to say that last season appears to be some kind of outlier, because the number of teams in the top block is much bigger than in recent seasons. And again, one might imagine that might have been due to COVID, basically. All right, so it's the final whistle then, here. And just to, no, let me, sorry, jump the gun slightly. I just wanted to make a couple of extensions to the framework. The model basically models these kind of categorical outcomes, win, draws, or losses. But in principle, we could model the number of goals scored in each game using a Poisson GLM framework. This is used quite a lot in the literature. So Dimitris and Yanis have worked on these models for years, And they've extended the bivariate setting, for example. So there's lots of extensions one could think of. All right, we now are at the final whistle. Okay, so match almost over. Here's a link to the archive version of the paper. And I also want to point out that there's a GitHub webpage that Francesca has put together where you can rerun the analyses or actually apply them to your own league and see what turns out. So it's a nice resource, and she's done a great job to put that together. All right, going to finish up there. So thanks very much for your attention.
Thank you very much, Niall. So I don't know if we have time for questions. Niall has already pointed out that he has another appointment at the moment.
I'm happy to take some questions, so I can be a really
So please, if Niall has the time, you can ask Niall.
Absolutely.
Yes, Labros.
Thank you for the nice talk, Niall. Quick question from my side is that can this analysis be extended to different types of championships, like, for example, a World Cup or a European National Cup, because the structure is different there over time?
Yeah, yeah. I mean, for those kind of World Cup, European Championship, Champions League situations where you have a league followed by a knockout, yeah, it'd be kind of hard to apply them there really, because I suppose some teams will play only a small number of games and they won't play against every other team. So in principle you could, but I don't think the conclusions would be that strong from it. Okay. But it is a good kind of question to wonder how you would kind of appropriately model that type of tournament situation. So it's a good question.
Cool. Yeah, cool. Thanks.
So another question from Bernard.
Hi.
Hi, Ben. How are you?
Hi, Niall. I enjoyed your talk, although unfortunately I missed a bit of it because of a technical problem. Two things. Our estimation of mixing weights part of your work? And the second question is, how many blocks are there in the Scottish Premier League? And finally, is Celtic going to win this year?
All right, I'm going to take the third question first because that's the easiest one, and that's a yes.
Right.
With high probability, I'm hoping.
Right.
That's a very biased yes. Ben is from Glasgow, and he's a fellow Celtic fan as I am.
Yes.
Scottish League balanced? I'd imagine it's very imbalanced.
Yes.
I'd imagine so. And then the mixing weights, yeah, they're incorporated into the model, although we don't estimate them, and they're integrated out, I think. Yeah. Yeah, I think we do, Ben. Yeah. Yeah.
I was wondering about something like the EM algorithm.
Yeah, I mean, I'm sorry for scrolling through here. Yeah, the EM algorithm is definitely one that could be applied to this situation as well, and it's used a lot in SBM models in the literature, so it could be used here as well.
Okay.
Just not something that we've pursued.
I will email you on this in more detail.
Cool. Nice to hear from you, Ben.
You too.
Cheers.
So Lida has a question.
Thanks very much, Niall, for the very nice talk. I was just wondering what approach you took for dealing with the label switching problem as the likelihood is invariant. Thanks very much.
Hi, Lida. Nice to hear from you. The likelihood invariance issue is dealt with an algorithm called Carpenetto and Tot, and it's one that's kind of suitable for this type of problem where you have a discrete variables, basically these allocation variables, and tries to minimize the a distance of some sort between two possible allocation vectors, so that
Okay.
so that if we find the kind of best permutation, that distance will be minimized.
Yeah. Thank you.
You're welcome.
Another one from Dimitris.
Okay, Niall, I know that you have to leave, and perhaps this question may start some discussion. So
okay,
if you have to leave, do it now.
No
okay,
problem.
so you have the scores, and you change the scores to the outcome, win, draw, or loss, in order to model. What about if, let's say, the y's are not the multinomial, the three categories, but it is the score? With some of the models that exist in the literature, how can we, let's say, go ahead with something like that? I see a lot of complications and difficulties, but could it be, let's say, a further extension of this approach?
That's a really great question, Dimitri. Actually, that was what I was trying to get at in the last where is it here? The last slide here. So basically, if we used you know, the Dixon-Coles type of model, or the you know, the Poisson GLM framework that you've worked on, basically where we have you know, for each team we'd have a home parameter, an attack, a defense parameter. What we would be saying practically is that those set of parameters would be the same for every team in a block. So you'd have, you know, kind of a block specific attack, a defense parameter. Now, we could no longer appeal to conjugacy in our model in that situation.
Is it? I'm not sure. I mean, because we do have some results that because of the nature, for example, the bivariate Poisson, and if your covariates are discrete, you can have some kind of conjugacy. Or at least you can have some very nice results. I mean, closed form things that you don't need MCMC.
Right.
We can talk it and I can share it with you.
Yeah, I mean, the kind of thing about conjugacy, it's nice if you have it, but it's not essential, basically.
Yes, it makes things much easier. But actually, what's going on with bivariate Poisson is that you have a generalized idea of conjugacy in the sense that if your prior is a gamma, your posterior is a mixture of gammas. So actually, the calculations are already there. So okay, we can discuss on that. Sorry, I know that you are.
No, don't worry. It's a great question. Actually, I mean, I think that's the framework that would be ideal to place this in as a, you know, the next version of this.
Okay.
Kind of
we will talk.
It's a very good question,
okay.
And yeah, it'd be great to follow up with you, Dimitri, on that. Thanks.
Okay. Thank you.
No, you're welcome. Thank you.
So I think we are all done, and let's thank Niall for his very interesting talk. Niall, thank you very much for your seminar, and hope that we will be in a position to see and speak in person at some point in the near future.
I'd look forward to that.
Okay, so thank you, and all the best.
Cheers. Thanks, everybody. Thanks for
Thank you,
listening.
Niall.
Thank you very much.
Cheers.
Thank you, Niall.
Bye-bye.